All right. Hi, David Bainbridge from Sienna Corporation. Thanks for showing up. First, a little bit of an acknowledgement. I'm the storyteller today, for the most part. I want to acknowledge Karthik, who's sitting over there. He did a lot of the work. He did most of the work, actually. And I just want to give that acknowledgement because I appreciate that. The next thing I want to point out is when people talk about machine language, it scares a lot of people. I begin conversations with people and someone mentions machine language and they tense up. It becomes a little bit of a black box. And I wanted to kind of demystify it a little bit and it's just math, right? And I read a book a while ago and it had a really good illustration about some of the artificial intelligence machine language or machine learning. And it involves a ball, so I brought one. And I need one volunteer. It's really easy. You just got to catch this once. Anybody want to stand up and do it? Come on. There. Thank you very much. So watch how easy this is. There. He caught it. Now, thank you. That's literally all it is. Machine learning, at least what we're doing, linear inferencing, is really just trying to solve an equation. And the human brain turns out to be able to really do that very well in real time. So when this gentleman here is trying to catch the ball, what he's doing is actually making estimation until he catches it. And the more often he catches it, he's been trained and he gets more accurate. And that's what we're doing here in machine learning. So it's really just math, solving math equations to be able to predict a result. When we started this, the plan for this presentation, the idea was to look at P4 INT, look at that data, and see if we can use machine learning techniques to predict something like hop latency around a P4 network. And then look at that, what we can do in that prediction, and compare it to what we might get with traditional network management polling. And as pointed out in the last presentation, you get different granularity of data in those different aspects. And then see, in terms of machine learning, if INT is giving us better predictability than traditional methods. And that was kind of the goal. And the stretch goal, if you will, was then to use those predictions for closed loop so that we could then make network changes to improve, lessen congestion, lessen hop latency. We didn't achieve all that. I'll give you that right up front as a spoiler. But that still is our goal, and we'll still keep looking and working towards that, even post this. For our sample network, we took what ONF is using in terms of their P4 stratum capability, a leaf spine network with various hosts involved. And we took that and their demo network, and we used pure emulation. It has a mixture of behavior models for P4 switches, simulated, and OVS soft switches. We essentially extended that and made it all P4 behavior model switches. And then we took these 6 hosts highlighted in red that are attached to that network and essentially made them points of where we ingest data and sync data, the P4 data, into a file in this case, which we can then do some data analysis on, at least to get our initial assumptions. And so when we're actually running these tests, what we're doing is we're using iPerf and we're just blasting away every host to every host to see kind of the information we're getting from INT. What we got originally was hop latency, and we're like, okay, we really wanted more, but that's what we saw. We saw in the data really just hop latency, and it shocked us a little bit, to be honest. But we said, okay, let's take what we got and figure out what we can do with it. The first question we had to ask ourselves was really, how do we present this data, represent this data, so that we can do analysis on it that has any meaning whatsoever? One of the guys on the team came up with this kind of scheme that we're using, a schema. And essentially, each of those hosts represent a collector, a sync point. So we have its identifier. We have a sequence number. In other words, each collector is keeping track of the different flows. Then we have the normal INT data. Timestamp, switch ID, the ingress port, and hop latency. And again, we are limited to hop latency, and it still confused us, and we'll get to that a little bit later. But we said, okay, what can we do with this? And so we pulled out the data, and it was something like 6 million lines of data, or records of data in a 10-minute sample. Huge amounts of data. And we started to plot this. And the first thing we said was, oh dear. Just visually, when I look at this data, I can't see any correlation, really. You know, you've got repeated patterns there on the far left. You've just got, values that are bouncing all over the place. And it worried us in a couple different ways. One, it worried us that we're not going to see the correlation we want to. And if we can't see correlation, then the machine learning techniques just aren't going to work. The second, and we did think we saw this, is we're seeing artifacts of an emulated network. Because we are using Mininet under the covers here, as we collect data, the actual hardware that it's running on is actually influencing the data we see. It's not a clean thing. And so one of the things, and I'll talk about that in terms of what we want to do next, is we need to get this on real hardware. Emulation of networks may not be sufficient for what we want to do, at least for testing it. But we soldiered on. And so as we did this, we said, okay, what other information are we getting from the telemetry that might be useful, that we might incorporate with hop latency to give us values? And the obviously next step was the path information. One value of INT is really, I understand the path the packet took through the network. And it seemed kind of intuitive that that path is going to influence the latency at the different nodes in the network. So we looked at how could we encode this path into our data such that we could run machine learning algorithms on it, do linear interpretation. So we came up with a mechanism. We essentially enumerated the paths and said, okay, how many paths are possible, and then we can assign, kind of bucket them in terms of a machine language term. And we came out with a way to bucket them. It wasn't quite the same as enumeration because we did have a limited set of paths across our network. And so then we tried to incorporate paths into our data correlation. And what we found out is that plus hop latency still didn't kind of give us the direction we wanted to go. Gave us a little bit more information, but wasn't really sure what we were going to get there. So we did a lot more charts, a lot more thinking, a lot talking, and we said, okay, let's look at some relationships between devices. And let's see, in terms of those paths, we look at micro paths, if you will, switch-to-switch connection. Are we seeing some correlations? And so what you see here is in this chart up that's right next to me, from the machine language tools we were using, machine learning tools we were using, which was TensorFlow, it was saying, look, there's a correlation between device 226 and 246 in terms of hop latency. So we plotted that data and said, okay, what's this correlation look like? And that's kind of the graph it looks like. It can see that correlation, but when you look at that from a human eyes, you're like, you know, that's a very weak correlation. That's not really going to help me in prediction because there's just a whole lot of outlying data. And that's just not going to give me what I need if I'm going to actually try to improve my network performance or my network, or eliminate my network congestion. You know, when the chart below it, the table below all this really is saying it's a correlation matrix from a TensorFlow or from machine learning technology. What it does is it looks at all the data you have, the various values you've got collected, and it says, am I seeing correlation trends between those two data? So you've got an N by M matrix out that. And so the one that's circled there, he says, look, the hop latency on 246 and the hop latency on 226 are related. That's all it's telling us. But again, when we looked at it in more detail, it wasn't really a correlation that we could use. So a real quick, kind of depressing thing that we came to real quick is hop latency isn't enough. And we went, okay, we're using INT, we're getting hop latency. It's not what we need. What do we do next? Fortunately, we found out very quickly we had made a mistake. We actually had more than hop latency. We had queue occupation. A value that we thought was queue occupation turned out to be an ID. And we thought, oh, well, great, we made a mistake. That's great. Let's move on. We have some more data. And so we said, okay, let's take this new data we have now and put it in our correlation, and let's see what we're getting out of this. And so here you see, in terms of switches, ingress, egress, and queue occupancy, are we seeing correlation between queue occupancy and latency? And you can see, particularly the different correlations, these are just different methods to determine correlation. We primarily use the Pearson one down there, and you can see there is absolutely, as you'd expect to be honest, a correlation between hop latency and queue occupancy. Specifically, it's at 0.78. Again, closer to 1, the closer the correlation. So we said this is good. What it means, if our target that we're trying to predict is hop latency, we have an attribute from the INT data that we can use to help us predict that. And we can use that, we can create a linear algorithm that will predict that hop latency. So we expanded this out. And what you'll find out in machine learning is what you do a lot of is data analysis, looking at charts like this, trying to find correlations. So we said, okay, let's take all our data, look at hop correlation, hop latency, and queue occupation, and find out where our correlations lie. And again, you can see there is a relationship between these two things in relation to how the switches are connected. And we still had to figure out how to work that in. But we said, okay, even without that, there's definitely a correlation between these two. So let's start generating some charts on this data and figure out what we can predict. So when we graphed out queue occupancy against hop latency, and this is over all the switches in this case, it says, are we seeing something where, at least from a human eye, I could look at that and say there's a correlation, I could draw a line, and if I can draw a line that kind of fits the data set, then I can do a prediction. We did that, and we said, well, that's pretty scary, because yeah, you can see kind of a trend, but from a prediction point of view, you once again have a lot of outlying data. And so the question is how to clean up this data. And so one thing we did is we said, okay, let's break it out. Let's look at it per switch information. And you can see in this case, all switches except one are fairly clean, or a little cleaner. And we have one switch which actually has data all over the place. I mean, there's a general trend, but there's still a lot of outliers. And this says, well, we have to do some cleanup of our data. We have to look at histograms and take outliers and clean it up to do our analysis. And that's what we continue to do. We cleaned up that data, and then we said, okay, let's take that data that we have now, occupancy to latency, and let's see if we can create a predictive model, linear predictive model. And in terms of TensorFlow, what you do then is you take your data set and you train a model. And training a model is all that's really doing is you're saying, I have a linear model with a bunch of variables, and I'm going to give weights to each of these variables so that I can fit my line to the data. And the trainer, when you train the data, it's basically TensorFlow going through multiple iterations and trying to get those weights on each of those variables a little closer to predict accurately. So it's essentially saying, okay, let me try this weight. That didn't work. Okay, let me change it a little bit. Let me try this weight. That didn't work. Let me change it. Maybe I got closer, maybe I got farther away. And the idea is as you get closer, your error rate decreases. And that's what you can see here mapped out as a root mean squared error versus the iterations of the algorithm. And as that error tends towards 0, the closer you can get, the better your prediction. And then once you get that, you can actually start prediction, and that's what we did. So, actually, let me go back. We still felt there was an aspect of the path that we needed to incorporate in this model, and we hadn't yet. I mean, if you look at the two graphs here, the first one, which is without path, it converged very quickly, which is good, which is what you want to see in a machine learning prediction. When we incorporated path, it converged much slower, which was a little troublesome. What this tells me, and it tells me in conjunction with some of the next graphs, we haven't quite figured out how to get the path correctly integrated into the machine learning. I still feel that it's there, it needs to be there, but the data's not telling me that. So it might just be a human bias that's telling me it's got to be there. And that's another thing you have to watch out in machine learning is don't let your human biases influence the data. And so that's still a risk that we have to deal with. So we did chart this, and here you see the greens are the actual values in our test data set, the reds are prediction. And in general, we're predicting the right thing. Our error rates are probably higher than what you'd want to see. But in general, we're going there. And again, when we predict and we add, this is with the path component, you can see our predictions there. And actually, if you look at that graph, I'm kind of happy with that graph. It's a little better, but it's not perfect. There's still a lot of outliers. One of the things that really still concerns us is, how much of this artifact as we're seeing is because we're doing emulation. And that's one of our next big pushes, is to get onto real hardware. But we continued on. We said, okay, now that we've kind of got INT in there, part of the premise of the presentation was going to be, well, how's that work in relationship to some of the more traditional data? So what we did is, rather than just focus on the traditional polled data, we kind of tried to mix them together. And so what we brought in were the metrics that we could pull out of ONOS during this. So ONOS has packet in, packet out, error rates, those type of things. So we tried to pull this information in. And what you see behind it is, when you take kind of denormalize the whole data set, a very large table. And I just zoomed in on a little bit here to what you can see. And what it really says is, okay, on any given switch, you see blocks of correlation. And when you dig down behind that data, what it says is, on any given switch, when we look at the data, there's a lot of zeros. The zeros tend to correlate with zeros, so that doesn't really tell me anything. When you look at cross switch, you see very little correlation when you bring in these error rates. So unfortunately, when we brought in the ONOS data, it didn't really add any value to what we were doing. That, again, it is somewhat counterintuitive. And again, it's not quite sure how much of that's because of emulation versus actual network. So kind of a post-mortem on this situation, and after post-mortem comes what do we want to do next, was what did we learn? Well, as pointed out even in the last presentation, the volume of data you get from INT is incredible. 6 million records in 10 minutes on an emulated network. That's a lot of data. More data than anyone's going to manually sift through, and that's why you need these type of algorithms. But it also says, when I start putting this in production, I can't run it at that rate. I've got to do sampling, and that was talked about in the last presentation as well. How do we determine when to sample, what to sample, how to trigger the beginning of samples, and move forward? So that is going to be a key aspect as we go forward. Knowledge acquisition was other key thing. We said, look, we trained it on this network. If I go and put it on a different network, all this training data is pointless. My correlations change, my relationships change. So like any machine learning algorithm, you have this context that it tries to operate in. And when you try to move that, what it's learned from that context to a new context, how do you transfer the knowledge? And it doesn't always transfer. And the problem with that is, does that mean I have to retrain, redo a data analysis every time I move to a different context? And that's quite problematic, and something that has to be addressed. Finally, to answer the original question, did INT help me? Was it really that valuable in terms of machine learning? Well, certainly more data, but it's unclear today that I got anything out of it. And again, part of that is emulation. I honestly think the data's there, and I think as we move from emulation to real hardware, we'll get better data. So, Barefoot, ONF, we'd love to partner with and get some real data and drive that. So, but it also points out that INT can't be your sole source of data for this. You're going to have to pull in multiple sources of data. INT will be one, metrics from traditional polling services will be another, and then that's got to be correlated together to get the final result, and that's something going forward we need to look at. So where do we really want to take this? There's a lot of upfront data analysis that we had to do. To make machine learning palatable to the masses, to be useful to production environments, we have to figure out a way how each company doesn't have to bring in a team of data to do all the analysis. So we've got to automate some of this. So one thing we've been playing with, and Karthik's been working on, is how do we make an adaptive machine learning model? What this means is, great, let's train it up front, take a model that we've just devised, put it in production. While that model is running in production and predicting whatever we need to predict, a target, a hop latency in this example, we also want to reevaluate the data as it comes in, and reevaluate it in a couple ways. One is, say, based on the data we're getting, are the feature sets we're trying to correlate still correct? And look at those correlation matrix and run kind of a best practices of data analytics, getting rid of, cleaning your data, getting rid of outliers, running correlation metrics, and maybe predicting new features that we're going to correlate on. Also, retrain that. So essentially, in the background of your production, your model's changing dynamically and picking these correlation features dynamically and generating a new correlation model, predictive model. And then use that model in the background and push production data through it as well. So you've got your production model that's actually doing your predictions, going to influence how you're going to potentially change your network. At the same time, you've got one or more candidate models that are also doing prediction. And at some point, perhaps, your candidate model's error rate is lower than your production model. And at that point, you swap. You essentially promote your candidate model to production. And so rather than have kind of a one model that you expect to run from here to eternity or until the next time you do a lot of manual work, you kind of have this automated process of continual model change and continual correlations. And so that's one thing we want to get into, and we've actually started. The second thing we want to get into, and this is even more fanciful, if you will, is the closed loop. We didn't get to this in this experiment. It just, time ran out, lots of different reasons. But we want to get to the point where the closed loop change to your network models how your operators work. So today, a lot of times when you're looking at closed loop, someone's built a policy engine. Someone says, okay, on this trigger, some policy is going to be triggered. That policy determines a change. That change happens, whether that's blessed by an operator or not, completely up to given deployment. But we kind of thought, it's like, how do people learn to do a task? If I bring a new network operator, how does he learn how my organization works? He watches. So one thing we thought about is, how do we take this model and apply it to network management with machine learning? Well, if a machine is sitting there predicting hop latency, for instance, and if operators are there watching those predictions, and based on that data they're seeing, they then make a network change, can we essentially have something observing that? When the operator does a CLI change, does an API through a change through an API or GUI, somewhere there's a trace of that change happening. Hopefully it's an API call. Any good management system better have an API. Now, if the machine learning can monitor those changes and has the context of what the network looked like before that change, the machine learning algorithm now has a pattern. See this pattern, perhaps make this change. And then you can use other machine learning techniques to say, okay, if he sees that pattern multiple times, that's a higher probability of that's what I want to do. And again, it's a game of probabilities. And so now what you have is the system organically can learn how to close loop the predictions, the changes you should make to your network based on your current operators. And that way, when I deploy in one operator versus another, it will actually adapt to your environment. That's kind of a research area, kind of a fantasy, but at one level it makes sense. Will it pan out? Love to find out. And I think it has that ability to say, look, we're going to do this organically. We're not going to have some expert sitting in a dark closet trying to predict what the best policy is. We're going to follow your operations model. And that goes into even a more adaptive machine learning kind of algorithms. We talked about where we got better linear predictive models. That's kind of, in a human form, that's kind of the spinal cord, right? You apply a candle under your arm moves. That's a reflex. And that's kind of what the linear interpretation is. And when you have a artifact that doesn't fit that, or data that doesn't fit that, then you have to bring it up to higher level learning, kind of the cortex of a human brain. And that's what we see in terms of machine learning here too as well, is you have to bring that, if it doesn't fit the reflex, it's an anomaly, bump it up to a higher level learning process, whether it's deep neural networks, whatever, building new models. And then hopefully as you see repetition in those higher level models, you can create new reflexes and continue on. So I think beyond this, you get this machine learning, adaptive machine learning program that leverages things like INT, leverages things like information from ONOS for the packet, for OpenFlow from the packet in, packet outs, and can hopefully get some of that closed loop capability within machine learning. Couple things. I pulled a couple quotes just because, well, there was some frustration and the quotes fit, right? What we're trying to do in machine learning is really look, there's patterns in the data. And what we want to see is how can we extract those patterns from all the noise of the data. Again, right now with the INT and the emulation, we're seeing a lot more noise than we should. So it's a lot harder to detect the patterns, and hopefully with the real hardware, we'll see less of that. Second of all, your machine learning is only as good as your data in a sense. And I'm not trying to say INT is bad. I think INT is very valuable actually. Getting the path, getting the low, the hop latency, getting the very fine-grained data, very valuable. But it's not enough. We need other data. And so it's just one data source as you get into machine language, and there'll be many, many more. And that's it. And I have probably 2.5 minutes for questions. Silence. Everybody wants beer. That works for me. Feel free to question me anytime if you see me in the halls, and enjoy your beer if there are no questions.